Hi everyone, this is my first PyData, so I'm super excited to be here. I'm going to be speaking about causal reasoning and Bayesian inference. So if any of you are interested in following up in more detail, I've got a repo for the talk, which you can go and find here. And because I was actually super productive and got more work done than I thought, this talk is also a package announcement, so great news. So I am Ben Vincent. I grew up in Cambridge, England, and I've been living in Scotland now for some time. I have just come out of 15 years in academia, and now I have an industry position. And so I've completed what could be called the golden tetrad. For a little while now, I've been contributing to open source with the PyMC Bayesian library, and I've been doing consulting work with PyMC Labs. Now, you may have heard that causal inference is so hot right now. And if you haven't, hopefully this talk will convey why that might be the case. But as a good ex-academic and data scientist, I thought that it would be good to evidence this claim with some data. So I typed in causal inference into Google Trends, and after initially getting excited about a peak in interest in recent times, I realized that this was actually due to a change in data collection methodology. But if you squint and step back from the screen, you can see that there might be a slight slope here. But is it convincingly there or not? So it was time to break out some statistics. So I ran a simple linear regression with a dummy variable for this change in data collection methodology. And the important result here is that we got a significant slope. And what this allows me to say, roughly, is if we theoretically ran this experiment an infinite number of times, there is a 5%, there's a less than 5% chance that the test statistic would be as extreme as the observed test statistic. And that there, in one sentence, is why I'm not a frequentist. So as a good Bayesian, I did the same thing, but with a Bayesian model using PyMC. And the result is pretty much the same. But now on the right-hand side, you can see that we get a posterior distribution over this slope. So if I ask myself, is this slope positive? Then the answer seems to be convincingly yes. But I can answer that using more straightforward language, saying that I'm 94% confident that the true increase in interest in causal inference is roughly between 0.03 and 0.08 units per month. And I can hear the skeptical among you saying, Ben, that doesn't really justify causal inference being so hot right now. And you might be right. You might think, well, it's lukewarm. But the Google Trends is a lagging indicator. What about the future? If we do some Googling, we can see that Gartner have placed causal AI right at the start of the hype cycle. And if you don't know the reasons why, then hopefully I can convey why there's a lot of interest in causal inference, causal reasoning at this point. And in order to do that, we have to think a little bit about the difference between statistical relationships and causal relationships. Statistical relationships are generally quite easy to establish. Observational data are pretty much sufficient. We've got a really broad range of statistical and machine learning approaches available. And because of that, we've got a lot of expertise in the data science community to establish statistical relationships. On the other hand, establishing causal relationships is very hard. It often, but as we'll see later on, it doesn't always require randomized control trials or experiments. But I think at this point, there is much less expertise in the data science community, and it also requires much more care to be taken. when you're examining statistical relationships, a typical approach might create a descriptive model where you essentially take in a bunch of predictor values and you pass this through some possibly complicated black box function in order to get your predicted output. Whereas when you take a more causal approach, you try to make a more open box model where the causal relationships have directionality and the details inside the box really matter. Now, statistical relationships, establishing statistical relationships is, and I think always will be, very useful because it allows you to predict things. And a lot of us data scientists spend a lot of our time doing prediction, and that's going to carry on being useful. However, the concern from the causal side of things is that if we make an intervention in our system, if someone goes in and changes how something works, then potentially your predictive model could break catastrophically. If you have taken a causal approach to modeling, then hopefully you are at a much lower risk of that happening. And so you should, hopefully, if all works out well, be in a better position to answer questions where interventions are made. So you should hopefully be able to ask what if questions, like what if the UK had not voted for Brexit? That's something that happened in the past. Or you could say, what if I halve my advertising budget next year? Now, to flesh this out in a little bit more detail, we're going to look at a miniature simulation that I ran where as a British person, it had to be about tea. And so we were interested in a possible causal relationship between tea and death. So I simulated an admittedly silly example where I simulated 5,000 people, and we look at which of those people drank tea and which of them died during the simulation period. And what we see is that of the people who died, a very large proportion of them drank tea. And so if we look at this statistical relationship we've derived from observational data, this would be really concerning if I hadn't simulated the data, of course, and we might think people should stop drinking tea. But then to make the point in my little simulated world, I conducted a randomized control trial, sometimes known as an A/B test. And in this version of the experiment, again with 5,000 simulated people, I randomly assigned them to drink tea or to not drink tea. And I saw who died and who didn't die. And in this case, roughly the same number of people ended up dying. But what we can see is that, if anything, tea might actually have a mildly protective effect, because of the people who died, most of them actually did not drink tea. So this is very confusing. Why is this the case? First, we think that tea might kill people, and now we think that tea might have a protective effect. Well, that's because I created a contrived example where there was a confounding variable of age. So in my simulation, older people are more likely to drink tea. Older people are more likely to die. Because of that, the people who died tend to be those who drink tea. But that is purely observational, and we can't make a causal claim about that. But if I come along now and do my random assignment, what we do is we break the relationship between age and tea. And so the probability that anyone will drink tea is now entirely up to me as an experimenter. I'm making an intervention. And this is exactly the case that could be problematic if we just look at statistical relationships. Now, even though random assignment is really good and really useful, it doesn't overcome death. And so it is still the older people who end up dying. And so in this simulation now, what it looks like mirrors the actual reality of what I simulated in my contrived world, in that T had a mildly protective effect. Now, you could say, okay, randomization is great. You've convinced me of that, but we are data scientists. We're not scientists in university. So can we not kind of solve this by modeling, by doing clever modeling? And the answer to that is yes, kind of. So if you think about your problem of T and mortality rates, and you think hard and you think that age might be a confounder, I'm going to take this into account and I'm going to measure it in my study. You could then create a Bayesian model which reflects this story of the data. And if you do that, you find that you can correctly infer that T has a mildly protective effect in this made-up data set. So that's great. That's good news. Can we just do modeling rather than experiments? Well, the answer to that depends. And it depends on whether we have actually captured the full story of the data, the full data generating process. In this example, we fixed our problem by taking into account our confounding variable of age. But in real examples, there might be many more confounding variables, and the story of the data might be much more complex. And the concern is that you never know if you have the correct or an accurate story of the data in mind when you model it. And that is why randomization is so effective. Randomization and A/B tests should always be the first port of call if you want to make causal relationships, if you want to make causal claims. The problem, though, is that you can't always randomize. And this is a problem for a number of different reasons. A big one is that randomized controlled trials can be costly. So both in terms of money, but also in terms of time. And they can often require very large sample sizes. And all of these things together actually combine in a slightly negative way to create vested interests, which might subtly bias the outcome, especially if profit is involved, for example, or scientific kudos. Another reason why randomized control trials might be difficult to do is ethics. It's not always ethically okay to assign people to conditions that you think might harm them. And in fact, even the opposite, you could argue that it's ethically problematic to not assign people to conditions that could benefit them. Also, randomization can sometimes be impossible. Sometimes just because the data that you have collected was actually collected in the past by other people who didn't use random assignment. But sometimes you just can't randomize, for example, which individuals are exposed to linear TV advertising, for example. And so if our boss comes to us and says, hey, I heard that causal inference is so hot right now, I would like you to infer the causal relationship of last year's advertising budget on customer signups. You might be tempted to hold your head in your hands and possibly resign, because you can't do a randomized control trial in this situation. And you know about all the problems of confounding variables and more. So what should we do? Should we cry or quit? Absolutely not. We should instead go and buy a coffee and a copy of Quasi-Experimentation by Charles S. Reichardt. Quasi-experiments, there's a whole family of quasi-experiments, and these basically outline a whole set of different designs and corresponding analyses which can be used in different situations that you might find yourself in, depending, for example, if you have many repeated observations over time, like sales over time, or if you do or don't have control units, for example. So this is cool. This is great. We can go and read this book and get to work. The problem is quasi-experimentation and the analysis of the data is new to a lot of people. So wouldn't it be really useful and really great if there was a Python package which could help us with this task? Fear not, there is. So today I'm doing an announcement of the CausalPy package. So you can go and check out the repo. So as I say, we have a GitHub repository, we have some docs. So it's good. We would like people to go and check it out and give us some feedback. But we also have a number of issues. We're at a very early release, and so do not put this in your production code at this point. So at this point, you might be asking, what does CausalPy do? So I'm going to show you a worked example of making a causal claim in a quasi-experimental situation. And something that plays on people's minds very often is, what was the causal impact of Brexit? Many claims were made by both sides of the argument and continue to be made. And so wouldn't it be great if we could empirically evaluate the effects upon the UK's GDP that happened after Brexit? Now, this is fundamentally a counterfactual question, because what we have to do is we can compare the UK's GDP with the counterfactual of what would have been the UK's GDP had the referendum vote gone the other way. Now, I don't have a time machine or access to parallel universes to go and get that data. And so we have a fundamental problem here of how do we get a comparison? And this is what quasi-experiments can help with. So practically in CausalPy, you start by importing the package, of course, and you can import GDP data. So this is actually available, real GDP data that I got off of an economist friend. So you can download that data set and play with it. After some very simple pandas manipulation, what we end up with is a data frame of GDP for a whole bunch of different countries, more than I could fit on the screen over time. And this is expressed in units of billions of US dollars. If we plot this, what we can do in order to make it meaningful is we can plot this in comparison to when the referendum vote announced. So the GDPs of all of these countries was normalized to 100 at that point. So the big red line shows what actually happened to the UK's GDP. And we can see that before the referendum, the growth in GDP was roughly in the middle of the pack compared to the other countries. After the referendum the vote was announced, we can see that just visually we're maybe at the bottom of the pack. So we also have other things that happened, which is worth bearing in mind that people might want to ask me about at the end. So we've got a whole bunch of data, but what do we not have on this graph? What we do not have is data from the parallel universe, the counterfactual of what would have happened to the UK's GDP if the referendum vote had gone the other way. And that is solved, or one approach to doing that, to estimating the counterfactual, is given by a method called synthetic control. And it does exactly what it says. So we don't have a control UK, which is similar in all ways to the UK other than it didn't vote for Brexit. So we're going to create a synthetic control UK. And we do that by estimating it as a weighted sum, a weighted combination of the control countries that we have before the referendum. So the training data. And the second thing that we're going to do is to create our synthetic control. So that might be the blue line. We're going to use the weightings that we estimated before in order to generate our synthetic GDP prediction. And just to be really clear, this is some kind of scikit-learn type of syntax. What you could do if you have a weighted sum model, what you're doing is you're fitting these weightings based upon the training data, or the data you have before the intervention, before the Brexit vote. Then in order to create the counterfactual, you're using that same model with the same weightings in order to predict what the UK's GDP would have been based upon the training data of other countries. And by doing this comparison now, you can estimate the causal impact of Brexit. The next step is to create a model formula. So some people might be quite familiar with this, but all it really says is that we want to model the UK GDP column given the data that we have about all the other countries' GDP. We can call the synthetic control method from CausalPy, and we've got this pretty simple API here where we provide the data, we provide the treatment time, we provide the model formula that I just outlined, and we also provide a model to do the estimation with some parameters that don't really matter in our case. I should say that if you're interested in causal inference, but you don't know about Bayesian inference, then CausalPy allows you to use traditional ordinary least squares model fitting approaches, currently using scikit-learn models. But today I'm going to talk about using PyMC models to do Bayesian inference in this causal setting. So once you've run that, you might be interested in visualizing the outputs with this very handy plot function. And that gives you a graph and a nice figure, or I think it's quite nice. I hope you do as well. What we can see up the top left, we can see that the shaded region here, this is our model fit. So the synthetic control, we can see pre-intervention is actually a very good fit to the data, and we're getting an R-squared estimate of 0.96, which is pretty good. So that allows us to say that it's a reasonable proposition to model the UK as a weighted sum of a bunch of other countries. What we also get is an estimate of the counterfactual. So this is something that you can only obtain if you can travel into the parallel universe where the Brexit vote went the other way. But this is our estimate of that, along with credible intervals. If we look at the difference between the two, that allows us to estimate the impact on GDP. The middle plot shows exactly the same data, but now we're visualizing it in a different way, plotting the residuals, which hopefully make that a little bit clearer to see. And in the bottom panel, we can see the cumulative causal impact. So for some of you who are familiar with other packages, this has some similarities. But if we look at our estimate, we can basically say with 94% confidence, we think that the cumulative effect of Brexit is somewhere between about -3 and about -5 billion US dollars. And then you can say, well, is that a large amount of money or a small amount of money? How does that compare to the promises of the Leave and the Remain campaigns, and hopefully keep people accountable? But of course, I've been suggesting that things are incredibly simple, and that's not necessarily the case. So there is some more due diligence that you have to do that I don't quite have time for here. Now, CausalPy has a bunch of other features which I'll quickly talk about. You can use this in interrupted time series, which is very similar to synthetic control. But in the example that we want to know how many excess deaths was caused by COVID-19 in England and Wales, we can do a very similar thing. This is different from synthetic control because we don't have untreated units to do the same approach. But nevertheless, we can still use interrupted time series to come up with an estimate. And this is done with standardized units. So the result here of about 20 is not 20 people. That's on a standardized scale. We can also do the regression discontinuity design. So on the right-hand side, we see all-cause mortality in America as a function of age. And we're in particular looking at all-cause mortality around the age of 21. And that's particularly relevant because that is the time where people become legally able to drink. And so there's a whole chain of reasoning that allows you to essentially say that if you look at the discontinuity, if there is one, then this becomes very similar to a randomized control trial. And in this case, might allow you to say that the mortality rate increases by approximately 7 per 100,000, I believe. Another very popular quasi-experimental design is differences in differences. We don't have time to explain this example, but we cover that. Now, I so far have maybe led you to believe that quasi-experiments can solve all of your causal inference problems, and that is very much not the case. So if we start to think about the story of some data of did your advertising budget causally drive sales, you can think, well, ad exposure might causally influence purchases. The problem is you didn't directly expose adverts to people. What you did was set a defined budget and a strategy. Which advertising channels did you direct the money at? And so you're not in control, and you don't necessarily know who is exposed to the advert. You can also think of confounding variables. So some people are more fundamentally interested in purchasing your product than other people. And it could be that your advertising was targeted specifically at those people. And then you can think further, maybe there's seasonality. So this, in fact, might be a confounder on a confounder. Now, the specific diagram that I've drawn here isn't the relevant point. The point is that once you start building up a causal story of your data, you can see how things get complicated very quickly. And so this is why making causal inference, especially in observational settings, is tricky. Nevertheless, when you can't randomize, quasi-experiments are very often your friend. And we are releasing CausalPy in order to help with this. So whether you're happy with frequentist or familiar with Bayesian approaches, you can analyze data you get from quasi-experiments. So if you're interested in how CausalPy evolves, or you're interested in causality in general and Bayesian inference, then feel free to find me on Twitter. I also have a website, and I'd invite people to check out the repo. We're very interested in bug reports or feature requests. And if you're interested to see how causal inference and quasi-experiments might help you in an industry setting, feel very free to get in touch. Thanks.
Yeah, thank you very much, Benjamin. That was a great presentation. So we've got a couple of questions on here. The first one by Francesco. As in ML models, data seems to play an important role. Any suggested resources for how to properly design RCT?
Not off the top of my head. So the theory of doing randomized controlled trials and A/B tests is kind of relatively simple. You just want to randomize things, but I know that there are a lot of things that you have to check. For example, that each of your individual treatment units, maybe people, for example, don't communicate within each other, so that the assumptions of independence and so on are properly met. But off the top of my head, I'm afraid I don't. I'll get in the chat after this.
No worries at all. The next question from Emiliano. Why didn't you use diff-diff model?
Yeah. So we can do difference in differences. So I had a slide on that. Now the reason why I didn't do it for the Brexit example is because we do have quite rich time series data. So one of the things to be aware of as well is that these methods aren't necessarily totally discrete. There is some overlap between these methods. So there is a method called synthetic differences in differences, for example.
All right, great. That's interesting. So the next one from Narendra. Is the Wayne model basically training ML model to predict the pre-treatment GDP of the UK based on the pre-Brexit GDP of the other countries?
Yeah, that's right. So you take the GDP data of all the untreated countries, and you this was a really simple model where it basically models the synthetic control as a weighted sum, but you could have more complex models to do that. But yeah, what you've written in the question is right. Sounds right.
Awesome. So the next person is asking how to have an access to the slides. How would they be able to access the slides if they want to do so?
I will try to make them available, and I'll tweet it. I'll tweet about it.
Oh, great. I guess you shared your handle earlier on your slide, yeah.
Yeah, I'll go in the Discord after this as well.
Oh, great. Yeah. The discussions goes on from there as well. So yeah.
Great.
Last question from David. Could you please tell maybe how it's related to the causal impact, in case you know it?
Yeah. So we have a bit more information about that on our GitHub page. So it strongly overlaps with causal impact. The difference with CausalPy is that we aim to make this more general. So causal impact only uses it only targets synthetic control, for example, and it uses Bayesian structural time series in order to do that. But the package that we've released now aims to have broader applicability across a lot of other different quasi-experimental methods. Thanks for the question.
Awesome. And finally, from William, is interrupted time series very similar in idea to regression discontinuity?
Yes. So in answer to a previous question, I said how there's actually overlap between a lot of these methods. The way how I would say that regression discontinuity is slightly different from interrupted time series, because with regression discontinuity, you typically don't use time as your X variable, if you like. That would tend to be some other variable, whether that be age or, for example, spatial location. You could see how exposure to advertising varies across borders of countries or in different legal regions, for example.